So in the last chapter, we talked about the basics you need to understand the muscle contraction. And now I will tell you how the contraction on a molecular basic will work. So this will be a little bit more complicated, or it's not like complicated. It's much stuff compromised on one slide. So keep attention, and if you have any questions after this, please don't hesitate to contact me. So the first we have like 4 parts, and this is a circle. So at first we will start here at this face. We will have the cross bridges formed between myosin and actin. And the muscle contraction initiates with the release of calcium ions from the sarcoplasmic reticulum in response to an action potential. So you don't see it here, but you have an action potential which causes calcium. We talked about this in the last slide. So we have Ca2+, who is released, and these calcium ions will be here, and they will bind to troponin, and they will cause tropomyosin to shift and expose the binding site to the actin filaments. So if there would be no calcium into this part, the myosin head won't be able to connect here. So we need calcium to get free binding. So now, as calcium is released to the cell, the ATP is used, and we will have a connection between myosin and actin. So for the second part, so we will go from there to there, we have a cross bridge formation and the calcium role. So the exposed action binding site allows the myosin head to attach and form the cross bridges. So the calcium presence facilitates this interaction by altering the troponin-tropomyosin complex and is allowing the myosin to access to the binding sites. This happens here. And in the second phase, we have the normal contraction. It's like the power stroke of myosin, which we will have here. So now comes the real contraction. At first we needed calcium to get the binding site, to get myosin to connect to actin. So energized by the hydrolysis of ATP into ADP and PI, which you see here, we have ATP, which serves the energy for this contraction. You see the myosin head shifts into this direction. And after this, ADP and PI is released. So now the myosin heads pull the actin filament towards the center of the sarcomere, as you see there. And this power stroke generates force and shortens the sarcomere. Like you had the sarcomere here, and now it gets shortened. And here you will have the H zone, as you saw in the picture before. So at the next part, we will have a release of ADP and PI and the ATP role. So after the power stroke, ADP and PI are released from the myosin head, which you saw here. And this release results in a Rigor-like state, and the myosin head remains attached to the actin. This is so important, And I think that's so amazing that many people are thinking if there is a contraction and ADP and PI is released, that the myosin head will release from the binding site. But you will need a new ATP, a new energy model, you'll see here, to release the myosin of the actin. So you will need one ATP to perform the contraction, and you will need another ATP to release the actin of the myosin of the actin. So you will have this, as told it here, your rigor mortis. It's like when people die, they will the muscles of the people will stay in a like rigor state, because if you're dead, you don't generate ATP, and if one contraction is performed, the body has no ATP to release the connection, so the people will stay in a very rigor state after they die, because after the contraction you don't have energy to release the contraction. And this is the thing why you have rigor mortis. So if you're interested in this state, please Google it, how this one works. And after a while, yeah, the contraction will release, because the molecules like myosin and actin, they will degenerate if you die. So then there will be no contraction. But for first time after you die, you will have in your body a real muscle contraction, which will not release at first. So only the binding of a fresh ATP molecule to the myosin head is essential for cross-bridge detachment, which you see here. So, and for the next one, you will have the ATP binding and the cross-bridge detachment and the calcium removal. So the ATP binding causes the myosin head to detach from the actin, which you see, what you see here. So you have ATP, and now the myosin head will release the connection. And ATPase activity on the myosin head hydrolyzes ATP into ADP and PI and is releasing the energy. So this energy is used to reset the myosin head's position, preparing it for another power stroke. And additionally, the calcium removal is initiated as the action potential ends, leading the repositioning, sorry, have problems with that, of tropomyosin, which covers the binding sites on actin, and this process begins muscle relaxation. So at the last part, myosin uses ATP to return to its erected state. So you will have another one. And then this will begin. So in summary, the actin-myosin sliding filament theory, which you saw here, involves a coordinated interplay between calcium and ATP, as you see, calcium and different ATPs. Calcium's role in exposing actin binding sites initiates the contraction process, while ATP's hydrolysis fuels cross-bridge formation, the power stroke, and the cross-bridge detachment. The removal of calcium, as you see here, and the repositioning, I don't know why I have problems pronouncing this word, of tropomyosin contributes to muscle relaxation at the end of the contraction.